In this video, we're going to be looking at various kinds of problems you're likely to run into in a typical high school or first-year college physics class that involve friction. I'm not going to be doing much of the math. You've already got your calculators. You've done enough math. I think you can handle that on your own. But we are going to be looking at the setups. Our first one is a picture that we've seen before. Somebody is pushing a brick against a wall to try to keep it from slipping. There are some forces involved. We know that the reason we need to push is because the brick has weight pulling down. Make sense? And therefore it's going to need some friction pointing up to balance that out so that it doesn't slide down the wall. Therefore the person involved is going to be pushing toward the wall with their hands with an applied force, and the wall is going to respond by Newton's third law with a normal force. And so to work a problem like this, we do what we always do. We draw a free body diagram. Our free body diagram is going to be the brick. Let's make an assumption that we know its mass. We'll call that M. And so we'll draw our forces and label them. The weight pulls straight down. That's mg. The frictional force points straight up. That's F, which, don't forget, is equal to mu times the normal force. Our applied force points straight toward the wall. We'll call that big F. And our normal force is pushing straight out from the wall. You might say normal to the wall. And that's lowercase n. Okay? If we set up some axes, as we always should, the usual directions will suffice here because it turns out all of our forces are lined up with the usual directions, so why not use them? Now this object's in equilibrium, so the sum of the forces in both the x direction and the y direction are going to be 0. Let's take a look at the x direction first. The only forces in the x direction are the applied force and the normal force. The applied force, look at its arrowhead, look at our axes, that's positive and the normal force is negative. So we have F plus negative n is equal to 0, which gives us the important equation that the applied force is equal to the normal force. Okay? Which means if you know the applied force, you also know the normal force. Typically, that's not how it's done. Let's take a look in the y direction now. The sum of the forces in the y direction is going to be 0 also if we're keeping it from sliding. And so that's going to be mu times the normal force minus mg. Do you understand why it's a minus sign? If not, take a good close look at the picture, maybe pause the video, equals 0, which means mu times the normal force is equal to the weight. Now, that's our second equation. Here's the great thing about a problem like this and the fact that I haven't given you any numbers. Let's suppose we know the applied force. Then that means we know the normal force. Let's suppose additionally we know the coefficient of friction. Then we can compute how much mass can be held up with that much force. Or if we know the mass and we know the coefficient of friction, we can find the normal force and therefore find out how much force has to be applied by the hands. Or if we know the mass and we know the applied force, well, let's see, the applied force tells us the normal force. That goes down here. We know the mass. We can compute what coefficient of friction we need to hold the mass to the wall. So you can work these problems in a lot of different directions just by using the very same equations. Let's take a look at our second example. Well, it looks like the first example, except it's on an inclined plane. See if I can draw that here. Okay, we have a little bit of an inclined plane right here with some coefficient of friction. And let's suppose that the inclined plane is at an angle theta with the horizontal. Well, let's draw our free body diagram again. Okay, I'll do that over here. Here's our brick. Still has a mass of m. What forces are acting on it? Well, we know certainly gravity is acting on it, And ladies and gentlemen, gravity still points down. Okay, so we'll call that mg. But the hands are now pushing into the table, so they're pushing like this. That's F. The frictional force that's keeping it from sliding down the ramp has to be in this direction. And that, of course, is again equal to the coefficient of friction times the normal force. And finally, the normal force is pushing against the mass from the ramp. So there's our normal force. Now, 3 of the 4 forces are at an angle. Only gravity is up or down. And so our best bet in a problem like this is to rotate our axes, maybe like this. Perhaps have this as the x direction, have this as the y direction. It would have just followed as you lifted up the ramp. Now, 3 of the 4 forces are aligned with these axes. Only gravity is the odd man out. That's the only one we have to analyze into its components. So let's do that right now. If I start by drawing the component of the gravity vector that's perpendicular to the ramp, I think we learned in a previous video that that can be to our advantage. Okay, we'll label that mg sub y, and then arrowhead to endpoint, draw the component that's parallel to the ramp. That's mg sub x. Notice how I'm labeling them based on the x and y directions we established. And if you've drawn the perpendicular component first, this angle up here is going to be theta. It's going to match the angle of inclination of the ramp that we established. Now we have to look at the fact that, once again, the sum of the forces in both the x and y direction are 0. Okay, it's in equilibrium. So let's look at the y direction first. I'll just put a little colon right there. In the y direction, the applied force is negative, the normal force is positive, but the component of the weight vector is negative. And we have to pay attention to that. So there are 3 forces in the y direction. So we would write, you want to start with the positive one? Sure. So we could write N minus the applied force F minus mgy. Now mgy is the adjacent side of our right triangle here. Remember, that's a right angle right there, with mg as the hypotenuse. So mgy I can replace with mg times the cosine of theta. Now that's in equilibrium, so that adds up to 0. Okay, a little more complicated looking, isn't it? But that's okay. Typically we'll know everything we need to know and can substitute into the equation to make it work. Don't worry about it. In the x direction, how many forces do we have? Well, we have the frictional force in the positive x direction, and we have mg sub x in the negative x direction, and that's it. So we can write the frictional force, let me just write that as mu times the normal force, minus mg sub x, let me write that as mg times the sine of theta, is equal to, well, it's in equilibrium, so I can write that that's equal to 0. And there are our 2 equations. Now it looks confusing, but I want you to consider this. If we know the mass and the angle, and of course we know g, and we know the coefficient of friction, we can find the normal force. And then we can plug that normal force into this equation, and if we already know m and we know theta, we can find out how much applied force is needed to keep that from sliding down the ramp. And we can work other ways as well. If we know the applied force and we don't know the mass or the normal force, that's okay, because down here we also don't know the mass or the normal force, and we have 2 equations with 2 unknowns, and you'll be able to solve that as well. So those 2 equations would be the appropriate ones. Now, I don't expect you to memorize those. I wouldn't. I don't have them memorized. But what I do expect you to know is how to draw a free body diagram how to rotate the axes and how to analyze any forces that are not perpendicular or parallel to the axes. One further thing, sometimes in problems like this, they have the force pointed that way instead of that way. If that's the applied force right there, then you're going to have to analyze it also into a y component and an x component. And you're going to have to be careful to figure out which angle is the correct one. Which angle goes with angle theta on this triangle? Is it this one or is it this one? Use your geometry skills and figure that one out. Okay? All right, let's try our next example. Well, this one looks pretty familiar. We have a mass on a table with a hanging mass attached to a string with an ideal pulley. The difference between this problem and what we did before is that now we're going to have a coefficient of friction that is not 0. So we've added complexity to the problem. Don't worry, we'll still be able to do it just fine. Let's call this mass, we could call them M1 and M2, but I'm just going to call this capital M, and I'll call this one little m. And the way we work the problem, that's right, free body diagrams. Which one do you want to do first? Well, let's try capital M. Okay, we'll do the big one first. So here's our mass, big M, and now we have to look at what forces are acting on it. Well, of course, the string is pulling on it this way. We'll call that tension. And because of that coefficient of friction, there's going to be a frictional force pulling back on it, which we'll call lowercase f. Don't forget that that's mu times the normal force. There's also going to be weight pulling down. That's mg, capital M times g, and normal force pushing up from the table. And there's our complete free body diagram. Those forces look nice. So that means we can use our standard positive directions for this, and everything's going to be really sweet. So what do we have to look at? Well, Newton's first law applies to objects in equilibrium. Newton's second law applies to objects that are accelerating. This is kind of both. You see, in the vertical direction, the y direction, there's no acceleration. So we can write that the sum of the forces in the y direction is 0, Newton's first law. Now, what equation would that give us? Well, up arrow, we have a normal force plus negative capital M times G is equal to 0. That's a sweet equation, okay? But in the horizontal direction, it is accelerating. Mu, by the way, is a coefficient of kinetic friction, sliding friction. So in the horizontal direction, we have to write that the sum of the forces in the x direction is not 0, but is equal to mass times acceleration. Now the forces in the x direction, well, there are only 2 of them, and the tension has the positive arrow. So we can write T plus negative mu times the normal force is equal to not 0, but mass times acceleration. Okay, so there's our second equation. Now this is pretty nice. If we happen to know the mass, then we can find the normal force and plug that in here. We know the coefficient of friction. The problem is we don't know the acceleration and we don't know the tension of the string. We have 2 unknowns. But that's why we have a second free body diagram. And that's what we're going to draw next. If you want, you can pause the video and try to draw it yourself and come up with an equation. Don't worry, I'll wait for you. Okay, you're back, and I'm pretty sure you're going to be right. So here's our second mass. We'll call that M. That's a lowercase m. What forces are acting on it? Well, of course, gravity. So its weight is pulling down. That's little m times g. And the tension in the string is pulling up. And that's going to be T. Furthermore, it's going to be the same T that was up on this free body diagram. That's only true, by the way, that the tension in the 2 parts of the string are the same if this pulley is ideal, meaning no mass and no friction. That way the string doesn't have to do any work. If the string does have to do work, then those tensions might be different. Now we have to choose a positive direction. It's going to be either up or down, but it can't be literally either one of them. You see, once we've chosen our positive directions for the mass up here, that means we chose to the right as a positive direction. When this mass moves to the right, the mass here moves downward. So we have no alternative. We must choose down as the positive direction. That means the weight is the positive and the tension is the negative force. And so using the sum of the forces equals mass times acceleration, we would have mg positive plus negative t is equal to, notice it's the little mass, little m, times acceleration. And there's our next equation. And those are all the equations we need. Let me tell you why. If we knew the mass, we could find the normal force. We know the coefficient of friction and this mass, so all that's left are the tension and the acceleration. If we know the little mass, here and here, then all that's left are the tension and the acceleration. We have two equations with two unknowns. Leave it to algebra class. You know how to solve those. Pretty sweet. But again, there may be other things that are unknown. You still write the equations and draw the free body diagrams the same way, and you'll be able to work the problem. Just make sure you account for all the relevant forces. Let's take a look at our next example. Whoa, this one looks pretty mean. We have two masses, frictionless ideal pulley on a ramp at an angle of theta. What's going to happen? The answer is, without more information, we don't know. So we are going to have to guess. Let's call this mass capital M and this mass lowercase m. And what do I mean by we don't know? Well, it's possible that the big mass could slide down the ramp, pulling the little mass up, or it's possible that the little mass could start falling down, dragging the big mass up the ramp. We don't know which it is. You know what we have to do? I hate to say this. We have to guess and hope for the best. I'll show you what I mean when we get to the end of this. So let's assume that the little mass falls and work the problem based on that assumption. Okay? If you want to, you can try to draw your two free body diagrams, then come back to the video. I'm just going to plow ahead here and try to draw them. So let's draw the big mass first. Here it is. It's tilted. Its mass is m. What forces are acting on it? Well, of course, it has its own weight pulling straight down. We'll call that big M times G. It has the tension in the string pulling up the ramp. We'll call that T. It has normal force that keeps it from sinking into the ramp. We'll call that N. And it has friction. Now we're assuming that it's going to slide up the ramp, which, since friction always opposes motion, we're going to have to assume that the friction goes this way, which is mu times the normal force, which is why we needed to figure out the normal force. Based on this force, and this force, it seems to me that rotating the axes is your best bet for a problem like this. That means we're going to have to resolve the gravity vector into its components. Let's start by drawing its y component. So that means the y component is going to come this way. Draw an arrowhead. And the x component is going to go this way. Draw the arrowhead. So this is mg sub y. And this is mg sub x. Okay. Right angle is there. Theta is there because we drew the perpendicular to the ramp component first. And we learned that that allows us to say that the angle of inclination of the ramp is equal to this angle. And now we think about, is it in equilibrium in any direction? Is it accelerating in any direction? Well, turns out it's in equilibrium in the y direction. because it's not flying off the ramp and it's not sinking into the ramp. So we can write that the sum of the forces in the y direction is 0. The equation then would be, well, the normal force is a positive force. mgy is a negative force. And so that's going to be minus mg times the cosine of theta. And that's equal to 0. If you don't understand that, pause the video until you do. Those are the only forces in the y direction. In the x direction, it is accelerating up the ramp. So the sum of the forces in the x direction is not 0. It's mass times acceleration. And so what forces do we have in the x direction? Well, the tension is a positive force in the x direction. The friction is a negative force in the x direction, so minus mu times the normal force. And we're not finished. mg sub x is a negative force in the x direction also. So we also have to write minus mg times the sine of theta. And furthermore, that doesn't equal 0. It equals the big mass times the acceleration. And by the way, since we're talking about the big mass here, all of these m's that I've been drawing should be capital M's. Sorry about that. And here as well. We haven't even talked about the small mass yet. So there's one equation. There's a second equation. Man, it's looking messy, isn't it? Again, don't worry. You'll be given all the information you need. If you can set up the equations, you can work these problems. However, before we can do that, we're going to need a free body diagram for the little mass right here. And so, and this time when I make a little m, I'll actually mean it. So here's our little mass, little m. Forces on it, pretty obviously, the weight is pulling down. That's little m times g. The tension is pulling up. That's T. Down is the positive direction to correspond with the positive x direction here, which means our equation is going to be mg minus T, that's the sum of the forces, equals little m times a, little mass times acceleration. And there's our third equation that we'll need. Again, it looks really complicated, but it's not bad once you have numbers in these places. Now, what do I mean by getting an inconsistent result? If on this problem you solve this and you get an acceleration that's negative, that's a problem, because that means that this mass is falling and this mass is sliding down the ramp if you have a negative acceleration. Or actually, it means this mass is rising and this is sliding down the ramp. The reason that's bad is because if this mass were sliding down the ramp, this frictional force would not be pushed down the ramp. That frictional force would be pushing up the ramp to try to impede the motion. Remember, friction always opposes relative motion. And so if you get a negative acceleration, that means A, you're wrong, and B, you have to do the whole problem over again. That sounds terrible. It's not. All it means is this arrow points that way, and it means since the frictional force is now positive in the x direction, it means that there's going to be a plus sign instead of a minus sign right here. Other than that, everything else is precisely the same. You have to make an assumption. Maybe you can guess better. If this mass is 20 kilograms and this one's only 1 kilogram, then you'll assume this one falls. You'll point the frictional force that way. You'll have your plus sign here and everything will work out perfectly. But just remember, in a problem like this, if the acceleration you get is negative, it means you've done the problem with the wrong assumption and you have to reverse the direction of the friction vector. That's it. That's about as hard as a problem is going to get in first year physics involving friction. If you can understand this and maybe do a real world problem with some numbers in it, get those out of your textbook or from your teacher, you'll be doing just great in this stuff. Solid A's. See you next time.